Okay, we'll get started and let people join us as they make it in this morning. Any questions about the assignments? Undergraduates, you're working on assignment 5, refactoring and random search. Graduate students 9 and 10. 9 is the genetic algorithm. 10 is phototaxis. So one robot, every robot being evaluated in multiple environments. No, we're all good? Okay. All right, so let's get back to lecture. We are working our way through now our historical segment of the course. We started last time by looking at 2 different experiments which were published in the literature at about the same time in the mid-90s. These were the first 2 evolutionary robotics experiments, both pretty ambitious for the time because physics engines didn't exist yet, so everything was done with physical machines. As you probably realize by now, if you're going to evolve a physical robot, you need some way to bring the robot back to its initial state so you can download the next neural network and assess its fitness and so on. So we're looking at those 2 experiments today. We'll finish, there's only a couple more slides in lecture 7. We'll then move on to a pair of lectures called minimal cognition. So around the time or shortly after these first couple of experiments, there were a number of papers published where the goal was to try and boil down the body of the robot and the brain of the robot to be as simple as possible and evolve behaviors for those robots so that if you watched one of these evolved robots, it looks like it was doing something cognitive. So if you remember back to our very first couple of lectures, defining intelligence and cognition, it's a very kind of slippery term. It's hard to say whether something actually is intelligent or not. So for the authors of the minimal cognition experiments, they said, we'll consider our robot to be cognitive if you show this robot to someone and they don't know what's going on inside the robot, they don't know it was evolved, but they say, yeah, that robot is doing X, some behavior which is a building block of cognition. There's certain things that we need to do to get around in the world to be considered intelligent. We've talked about some of these: categorization, being able to distinguish friend from foe, planning, you have to be able to think ahead a little bit. So there are all these sort of building blocks that we would expect in an animal or a machine that we would consider to be intelligent or cognitive. That's the goal of the minimal cognition experiments. Make the robot as simple as possible, but the evolved behavior is clearly an indication that that robot is performing X, Y, and Z. And we'll see what those are. Okay. These minimally cognitive robots are equipped with a particular kind of neural network, which is a bit of a mouthful, continuous time recurrent neural networks. We're going to talk about these CTRNNs in depth in lecture 8 today. The equations describing CTRNNs at the beginning look somewhat complicated, but as you'll see in lecture 8 today, they're not that different from the neural networks we've seen so far. And then probably on Tuesday we'll talk about the actual minimal cognition experiments, where we had where we have a very simple robot and we're evolving CTRNNs for those minimally cognitive robots. Okay, so let's go back to lecture 7 for a moment. We were talking about these first 2 experiments. The first one we saw was carried out by these Italian researchers using this little hockey puck type robot, the Kepler Robot, that was running around through the maze on a tabletop. We ended last time by talking about the Gantry robot, this kind of odd-looking robot which was built to make it easy to automate the evolution of behavior for the robot, right? They could send commands to the X and the Y trolley to bring this inverted periscope back to an initial position and then download another neural network on it, see what the robot does, and so forth, right? Okay, so as you'll remember, this inverted periscope robot has 7 sensors, the 4 touch sensors, and then these 3 visual sensors, these 3 fovea, or these 3 circles, that evolution can place anywhere inside the robot's camera, inside the robot's field of view. These circles can be at different positions and they can be different sizes. And at every time step of the evaluation of a single robot, we take the average grayscale values of the pixels inside those circles and average those grayscale values inside each of the 3 circles. So at the end of that time step, we're outputting 3 numbers, or 3 integers actually, which is the amount of darkness in those 3 circles, right? So this robot can see. It can't see much, but it can definitely see, right? It can see and it can sense using these bump sensors. Okay. And we've got 2 motors, which is the movement of the X trolley and the movement of the Y trolley. There's a 3rd motor, which is spinning that dental mirror, but we're going to assume that it's just always spinning at a constant rate and producing this 360 view around the robot. So 2 motors, 7 sensors, 2 motors, right? Okay, so the periscope is hanging down inside this hollow table. So the circle here is our little dental mirror, or the end of the periscope. And we want the robot to move in particular ways. And the first thing we want the robot to do is we're going to move the periscope to 4 initial random positions. And there's a black piece of Bristol board in the back there, which is our gray rectangle. And the robot has to always move to the black Bristol board no matter what the initial condition is. Pretty simple, right? We're going to use this idea, and we're going to see this several times throughout this course, of incremental evolution. We're going to start with a simple fitness function, which is easy for evolution to find a controller to solve that fitness function. And then as the generations pass, as evolution continues, we're going to replace our initial simple fitness function with increasingly challenging ones. What would be a good description of phi1, the first fitness function? So the robot moves, you download a neural network inside this robot 4 times from 4 different initial conditions. How would you assess the fitness of that single neural network? The grayscale values. We could do that. We're also going to just look at the position. So how close is it to the Bristol board, right? We could do that as well. It could turn and look at the black Bristol board, but still be a fair distance away from it. So we're going to measure the distance away from it. Okay. Obviously, it doesn't take that long to evolve a robot that does that, or evolve a neural network that does that. So in my little cartoon here, we have a neural network that causes the turret to move to the black Bristol board. Now, we're going to change the fitness function so that we're going to place a black rectangle either at the back right position or the back left position. So it can't just turn around and go to the back. It's got to go to the black rectangle. How might you change the fitness function now? Let's make things a little bit easier. Let's assume you have the position of the turret and the position of the rectangle. What's the fitness function here? Distance between the two, right? Pretty straightforward. Okay, so we do that for fitness function 2, and now fitness function 3 is going to be for each of the 4 evaluations of a single neural network. We're going to place either a triangle on the left, back left, and a rectangle on the back right, or a triangle on the back right and a rectangle on the back left. Could be either. And the robot, depending on where it starts, has to go away from the rectangle and towards the triangle. What might be the fitness function now?
The distance between the triangle is reward.
Yep.
And the rectangle is penalty.
As the penalty, right? So we're going to reward the robot for being close, or for minimizing the distance between itself and the rectangle and maximizing its distance to the rectangle, right? We could have maybe made this simpler and just said, well, if we're interested in getting to the triangle, minimize the distance between the robot and the triangle. But if the initial condition is placing the robot right next to the rectangle, the robot might evolve the ability to just move to the left. But we wanted to show that it's actually scared of the rectangle. So if we're penalizing for the rectangle as well, we want to see it move away from the rectangle and towards the triangle. Okay. There's different ways we could write this down, but here's a simple way to do this. So in the first case here, we're going to sum up all the fitness values for the 4 evaluations. Remember, like I talked about last time with phototaxis, if we're going to try and evolve a robot that's robust in multiple environments, we need to try out each controller in multiple environments and either take the average or just the sum of the fitnesses in that different environments. So y, you should write this as y sub I. This is the fitness of the robot in each of the in the ith environment. Simplest thing in this case is just perpendicular distance from the opposite wall, so the front wall. Right? We want to maximize the distance from the front wall. We're assuming everything is going to increase here. Next one, again, pretty simple, summing up over all 4 environments, the distance of the robot from the center of the rectangle. And as you pointed out before, in the third case here, again, we're summing up over all 4 environments. So we're going to take the distance, so the uppercase D is the distance of the rectangle or the triangle from the starting point, minus the distance, the final distance of the robot from the rectangle. So that we're taking the difference between uppercase D and minus D. Why? Why are we taking the initial position into account? So uppercase D is the initial position of the robot from either the rectangle, uppercase D1, or the triangle, uppercase D2.
Because you don't know where the robot's going to start.
Exactly, right? So it's going to be harder, again, if we place the robot right up against the rectangle, we're kind of unfairly penalizing that particular initial condition. So we're kind of normalizing based on where the robot starts, right? So let's look at the first term here, the D1s, right? So D1 is the rectangle. So we want to try and get this term to be as high as possible, right? So move away from the rectangle. And we're going to subtract any distance that remains between the robot and the triangle. Okay. Y alpha and beta here. So the investigators have added in 2 additional terms, and these are not dictated by the robot, right? Alpha and beta, the Greek letters suggest these are something that's outside the experiment. They're set by the experimenters. Why would they introduce alpha and beta?
Does that say you can weight the reward and penalty differently?
Absolutely, right? So they were probably playing around with alpha and beta a little bit to sort of, if you increase beta, you were increasing the reward for getting near the triangle, and by increasing alpha, you're increasing the penalty for being anywhere near the rectangle. Right? So this is, again, a bit of a tricky fitness function because we're trying to get the robot to do 2 things, go towards the triangle and away from the rectangle. So we're going to see a lot of fitness functions throughout this course, and often we're trying to find a way to write down this fitness function to get evolution to strike a balance between these 2 things. Or better yet, do both, right? Avoid rectangles and go towards the triangles. Okay, again, the specific form of each of these equations doesn't matter, but you can sort of see that we're gradually making things more difficult for the robot as evolutionary time proceeds. Right? The reason the researchers probably did this is they probably did version 1.0 of their experiment and just used this, and it didn't work, right? The robots couldn't find the objects, or they were always going towards the triangle and they might brush up against the rectangle. So they said, let's start with something simple and then gradually make things more difficult. Okay, we'll see a lot more of that as we go. Okay, let's have a look at one neural network that was evolved. So this was the best neural network they managed to evolve using the Gantry robot. Let's have a look at what the robot did first, and then try as best we can to understand how the neural network produced this behavior. As you know by now, we can't really get into the guts of this neural network and figure out what's happening, but we might get a little bit of an intuition for what's going on. Okay, so we're looking at the Gantry robot from above, triangle on the left, rectangle on the back, and you can see here's initial position 1, here's initial position 2, and I think initial position 3 is somewhere in here, initial position 4. What did the robot do from those 4 initial conditions? Is this the optimal behavior? Definitely not, right? Optimal behavior would be head straight for the rectangle, or at least curve your travel to sort of stay away from the rectangle as you approach the triangle. What can you tell me about this evolved behavior?
It likes to turn left.
It likes to turn left, right, for some reason. If you ran this all again, it wouldn't necessarily turn left. It might come up with something else. For those of you that have made it to the phototaxis experiment, you might have noticed this phenomenon as well, which is evolution tends to be pretty conservative, meaning that the neural network will get the robot to do more or less the same thing in all 4 environments, but gradually tweak that movement depending on the given environment. So left to its own devices, the Gantry, this controller in the Gantry robot causes it to kind of turn to the left. Not so much in this case, but you can see there's sort of an initial similarity between these trajectories. Probably because earlier an ancestor of this neural network, one of these 4 trials got the robot actually to the triangle, and evolution figured out how to modify that behavior for the 2nd, 3rd, and 4th trial. Right? Evolution isn't somehow packing 4 different behaviors into this one neural network. It has one behavior, one way of moving the Gantry robot, and that behavior, that movement is modulated by the sensory information. Okay, let's have a look now as best we can at the neural network. Remember that our robot has 3 visual sensors and 4 touch sensors, but only 2 are drawn. Why? Why are we missing the other 5 sensors in this picture? Remember, we're looking at
devices, right?
What's that?
There are 2 devices.
2 devices?
Yeah,
What do you mean by devices?
Like the touch sensor isn't actually 4 sensors.
The touch sensor isn't actually 4 touch sensors, right? We're computing it from that little bump, that little plastic circle, right? They're there, and they're producing touch information. They're just not being drawn in this final evolved neural network. Why not? The researchers didn't forget to put them in.
Do they take like the maximum of the touch sensor and the maximum of the vision sensor and only include those 2 in the drawing?
No, so we got visual V1 and V2 here. So 2 of the 3 visual sensors, 2 of the 3 visual fovea here, these circles. They also left out the 3rd circle. Why?
The robot didn't need them.
The robot didn't need them, right? So the synaptic weights that connect those 5 other sensors into the network were basically 0. Evolution got rid of them, didn't need them. All it needs, apparently, this robot, all it needs are these 2 visual sensors, right? Remember that evolution is deciding where to place the 3 circles and the radius of them. So evolution has evolved to place these 2 fovea here. It's also placed the 3rd circle somewhere, but the values that are being extracted from that circle and plugged into V3 never affect the motors. There's synapses with 0. There's information from that sensor never makes it through to the motor layer. So in the ScissorBot experiment, right, there's a position sensor in there that you're using to calculate fitness, but the position sensor is not wired up to the motor neuron. So the values of the position sensor don't influence how the robot moves, right? The robot can see, it can sense that information, but it's just throwing it away. It's not affecting its behavior, right? I can see the colors of your shirts, but it's not influencing the flow of this lecture, right? Okay. All right, so we can see a general flow of synapses through to the motor layer. So we've got the left motor and the right motor here. I can't see what this says up here. This might actually be the turning rate of the dental mirror. I might have misspoke. It might actually be able to control how the dental mirror moves, but it's not important for our purposes. What else can you tell me about this neural network? There's a few things in here that'll give you a hint about how this robot is able to approach the triangle and avoid the rectangle. Remember back to our discussion about neural networks, right? We have synapses, and most of the synapses are flowing forward from the sensors to the motors, but not all of them. What are the other ones doing? What are the other ones called? We've got our feed-forward synapses. What are we missing here?
Backpropagation.
Backpropagation is this learning method which propagates air backwards from the motor layer up to the sensor layer and changes the synapses as we go. But backpropagation has a problem with certain kinds of synapses. What were those synapses called? No? So in this case, evolution has added recurrent synapses, right? Recurrent synapses are ones that cause loops, right? They cause recurrence. You can see there's quite a few of them, not just causing loops, but also self-connections, and also some that are flowing backwards from the motor layer to internal neurons. These are the hidden neurons, which we also talked about, right? Hidden neurons are sort of hidden from the real world. They're not directly receiving information from the real world, like sensor neurons, and they're not directly influencing the real world like motor neurons. They're hidden. They're in between, right? So evolution is making use of some of those down here. What's the utility? Why do we have recurrent connections? What's their function? Remember?
What was it when we talked about the and/or, and so you could kind of compute more complicated things?
That's what the hidden neurons are for. So when we did the XOR function, we saw that we needed hidden neurons because hidden neurons allow us to create a nonlinear function. We compute those sort of two subfunctions, and or, and then we combine the results at the output layer to compute the XOR function. So we don't need recurrent connections to compute the XOR function. We need hidden neurons. What do recurrent connections give us?
Does it make it so that you can do something based off of what you previously did?
They give the neural network memory, right? So if you didn't have recurrent connections, right, just for a moment, just mentally erase all these recurrent connections, then the motors, by definition, have to change based on the sensor values. That's the only thing influencing the motor neurons. Sensor values come in, they flow through, and they affect the sensors, right? The only thing affecting your current behavior is what you currently see. You have no memory, right? If you have internal connections, let's see if we can follow this through. Here's a connection through coming back. So we're setting the values of the hidden neurons based on this back connection. And now at the second time step, new information comes in, new sensory information comes in, which flows forward, but so does the output of this little hidden circuit down here. So this motor is being influenced by this sensor, and also whatever is stored in this little circuit here. It's remembering information from before. We have no way by looking at this about what it's remembering, but it's remembering something. Okay, so we're already starting to tease apart a little bit about what evolution is doing here. It's throwing away a lot of information, a lot of sensory information, just keeping these two circles, and it's remembering something, but we don't know what it's remembering yet. Let's see if we can do a little bit more sleuthing here and figure out what's going on. Where is the recognized triangle circuit in here? Where's the recognize rectangle circuit in here? So this is not like the XOR function. We don't see sort of one part of the network computing, is there a triangle in my field of view? And another circuit that's computing, is there a rectangle in my field of view? And then combining those partial results. This is a pretty simple looking neural network. What is a triangle? If I were to ask you to describe it, what's a triangle?
Polygon with 3 vertices.
A polygon with 3 vertices, right? So there's one here, one here, one here, one here. You would expect to see 3 circles down here, right? Maybe the circles are looking for the vertices of a triangle. We don't even have 2 circles. We don't even have 3 circles. How is this thing, which can only see through these 2 circles, recognize a triangle or a rectangle? Seems pretty strange.
Is that why I wanted to like turn left all the time? Because the fitness function was rewarding it when it went to the left black.
So that's part of it, right? So definitely turning to the left is part of it. It's got these 2 circles. What's happening? We've got to put these 2 pieces together.
When it senses a rectangle, is it picking up darker average values in its vision sensors?
Okay, getting closer. So obviously, when it doesn't see either object, the brightness of these 2 circles is quite high. So V1 and V2 are firing at a high level.
Because if they have the same width and same height, the triangle would have like the area covered, so it would be picking up darker values for the rectangle.
Yes, getting very close now, right? So there's one piece of that your explanation that's still missing. What is it? So these circles are going to darken when it's turning to the left or when it's turning counterclockwise, and suddenly the circles start to go dark. It sees something. How does it know what it sees?
Isn't it picking up less light from the triangle? Because it's,
Less light in what sense? We're still missing one piece here.
well, there's less area to emit
At the
light
bottom.
from the triangle.
Less light at the
There's less light at the top.
less light at the top, right?
Oh, yeah.
So the little piece that we're missing in this explanation is time, right? The robot is moving, moving, moving. Both of these circles are white, 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 and it's turning and it hits the rectangle. So what happens as it's turning? Let's follow this guy here. It's looking this way. It doesn't see the rectangle. Turning, turning, turning. Sees the rectangle. At the moment it sees the rectangle, what happens here?
They both go off.
Not both. It's turning, turning, turning. One goes dark, right? It hits the rectangle, and then it keeps turning, and 2 goes dark a couple time steps later. Let's look at the rectangle. This is actually a poor example of this. Let's try and redraw this. Okay, let's use this one. So the base is at the top of the field of view. What happens now when this guy is turning, 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 and hits the right edge of the triangle? What happens to V1 and V2 here?
It takes longer for 2 to go dark.
Bingo, right? It takes longer for 2 to go dark. So 1 hits the right edge of the triangle, and then more time steps elapse before 2 goes dark than the rectangle goes dark. So this robot, even given the fact that it has a very, very simple visual system, can distinguish between triangles and rectangles, right? And then it somehow uses that difference information to figure out how to move. When I asked you what a triangle was, you gave the normal human explanation, right? There's 3 vertices and they're arranged in some relative position, some positions relative to one another. If you were to ask this robot what a triangle is, what would it tell you? It certainly wouldn't give you that explanation. What would the robot tell you?
Sensor 2 gets dark 0.5 seconds later.
Absolutely. So if you were to ask the robot, it would give you a sensor motor description of what a triangle is. When I asked you, you gave me a purely visual or geometric explanation if you want, right? There's this thing going on in my visual field. This is one of the first experiments in evolutionary robotics, but this started to change a lot of roboticists' thinking about thinking, right? Remember, thinking about thinking is misleading. If I were to, you remember back a few weeks ago, I showed you the picture of Marilyn Monroe, and we were talking about how you would recognize Marilyn against the black background and all that. You'd say, well, I know it's Marilyn because you give me some visual description of what she looks like, right? that's probably not what you're actually doing when you recognize Marilyn Monroe or a triangle or a rectangle. You look at some very small part of your visual field. The moment you look here, everything else is blurry. Based on what you see here and a little bit of blurry stuff on the periphery, your eyes jump or your eyes saccade to some other piece of your visual scene. And then you jump again, and you jump again, and you jump again. Probably what your brain is doing to visually recognize stuff is to say, I see this little piece of my world, and when I move to this position, I see something else. So your brain is probably using sensor motor information to recognize objects, but you're not aware that your brain is doing that. And when I ask you after the fact to tell me how you recognized this thing as a triangle, you would give me a purely sensory account, and you'd throw away the motor part of the puzzle. Right? Remember all the way back to the beginning of the course, we talked about René Descartes, and he separated body and brain. The body and movement and all that stuff, that's not so important. Us and how we see the world is important. We seem to have this very deep bias when we inspect our own behavior or our own cognition to think of what we're doing as a passive thing. I'm just this brain looking at the world, recognizing patterns, and so on. We seem to forget or not notice that there's a big action component in how we get around in the world. So personally for me, this is one of the things that's really interesting about not just robotics, but evolutionary robotics as an approach to understand intelligence in general, is that often evolution comes up with solutions that seem very non-intuitive to us, right? We know that a neural network can compute the XOR function. It could evolve some circuit that recognizes triangles and then another one that recognizes rectangles by actually looking for vertices and doing it in the way that we feel that we do it, and then combine the results. Evolution does not find that solution. It finds a simpler solution, which for us is non-intuitive, right? It gets us to think differently about how we think. Yeah? Okay, that's the first experiment we've seen that does this. We're going to see a lot more examples where evolution is going to challenge our preconceptions about what intelligence actually is. Make sense? Okay. Again, I don't expect you to remember all the details of this particular robot in this experiment, but the take-home message here is evolution explodes our preconceptions about thinking. Thinking about thinking is misleading. Evolution can get us back on track and understand what the nature of intelligence really is. Right? Okay, any questions before we move on? All right, so let's shift gears now. As I mentioned, we're going to now have a look at some minimal cognition experiments. These minimally cognitive robots are equipped with a particular kind of neural network called a CTRNN. So again, let's just review what we've seen so far. The simplest neural network that we've seen so far is that each neuron in the neural network, the ith neuron if you like, is at every time step set equal to something which is placed inside of an activation function. This activation function is always squashing whatever is inside here to some desired range. For most of what we're doing, this function is the tanh function, which will squash this thing to a range between -1 and +1. The simplest possible neural network we can imagine is this one, lowercase j equals 1 to uppercase j, where uppercase j is an integer indicating the number of incoming synapses to the ith neuron. And we're going to denote yj as the neurons that are influencing yi. And we've got one term here which is missing, one variable here which is missing. What is it? The weight, right, W, of the synapse. Of which synapse?
IJ.
We're going to write it as Ji, because this will remind us that this is the weight of the synapse that connects neuron J to neuron I. Right? Each one of our neurons, we're going to update it using this equation, and we now have new values for the neurons. In the case of robotics, we take the motor neurons then, and we send the commands out to the motors, and away we go, right? That's sort of the simplest possible thing that you can do. We're going to look at CTRNNs today, which are a little bit different, and they're more similar to the neural networks that actually exist in PyroSim. Okay, before we do, and I apologize for this, we're going to recap a little bit of calculus first. This is my cartoon example of where calculus came from, right? You remember that if we want to try and calculate how something changes over time, let's imagine for the moment that x is time here. So time is elapsing, and we're observing some variable y that's changing over time. We can sort of approximate this sort of thing by writing delta y over delta x. There's this kind of change in y, delta y, for each delta x, for each interval of time, right? It's a good approximation, but this doesn't work very well when we want not just an approximation, but an exact solution, right? How exactly is y changing as a function of x? So we can do this by making this interval shorter and shorter and shorter, and for each of those shorter and shorter intervals, explain exactly how y is changing. But there's a problem, right, which early mathematicians started to realize, which is what happens when delta x approaches delta y. So let's go back to our simpler case here. Let's imagine that we're just assuming that time is going to change from 1 second to the next. So this is x equals 1, x equals 2, which means at 1 second, and then at 2 seconds, and then at 3 seconds, what's happening to y? Well, y is also increasing by 1 for every 1 second. Let's imagine we're watching our robot moving. It moves 1 meter for every second, right? 1 second elapses, 1 meter, the robot travels 1 meter. We can write that down as a difference equation, right? The new position is, actually I think I have this wrong, right? It should be, oh, I changed my variables here, I'm sorry. They were x and y here, and then I changed them to t here and x here. My apologies. Okay, so x at the next time step, x is now meters at the next second, at second s at t plus 1 compared to s is 1, so it's gone up by 1. Okay, we can use this difference equation where we're writing the new value at a new time as a function of what it was before plus something else. But this doesn't make much sense when delta x approaches 0, right? So now our difference equation says x, the vertical axis here, isn't changing at all. But we can tell from this picture that x definitely is increasing over time. So our difference equation is failing now, right? So now we invent calculus, and we can now write a differential equation which says this is how much x changes as a function of t, without saying exactly how much t is changing, right? Okay, so most of what we've seen so far for our neural networks are actually, what we've actually seen for our neural networks so far is a difference equation, right? The new value of this neuron, neuron I at time t, is equal to the influence of the other neurons on it at, sorry, let me change my notation here. All right, so this is a difference equation, t minus 1. So the new value of y is some function of values at the previous time step. Okay. For most of what we're going to do in this class, you're going to be using neural networks which are written down as difference equations. In the CTRNN, and this is the C in CTRNN, we're going to use differential equations. Okay, so what we're going to do in the red box here as we go is I'm going to gradually start to fill out this equation here. So follow along with me, either a pen and paper or on your laptop. We're going to start to add these terms as we go, and we're going to build up an equation to describe our CTRNN as not a difference equation, but a differential equation. Okay, so the first piece of this equation says the value of neuron I is changing over time, and it's changing over time as a function of the negative of its current value. It's a little tricky, so let's try and do the geometric interpretation of what's going on here. Let's create a graph with time on the horizontal axis here, and y sub I on the vertical axis. So I'm going to start to draw some curves in this figure here, which is going to show how the value of neuron I changes over time. Yeah? Okay, let's put a little dashed line here. This is y sub I equals 0. This is +1 and -1. So we're going to assume our neurons can range between the values of -1 and +1. Let's set the initial value at t equals 0 of this neuron to 0. We haven't added in our other neurons at the moment. We're just using this very simple equation which says the rate of change of yi is equal to the negative of its current value. Let's say we set the initial value of y sub I to 0. What happens over time? How does the value of this neuron change over time? It doesn't change over time, right? So if the initial value of y sub I is 0, minus 0 is 0, so the rate of change is equal to 0. There's 0 change to the neuron. So with this simple equation, if we had a neural network, and set all the initial values of the neurons to 0, we'd get this, right? Nothing would happen. Okay, let's imagine now instead we set the initial value of the ith neuron to +1. Now what happens over time? We have our initial value, but we haven't changed the equation.
We bounce back and forth between +1 and -1.
Possibly, right? So we could change a huge amount at the next time step. What the piece I haven't told you is how to integrate this over time, right? So usually when we integrate our equations, our differential equations over time, we use numerical approximation. We're not going to get into that in this class. So we're going to just assume this is a continuous function. A continuous function meaning that at the next time step, it only makes a little bit of a change. The initial value is 1, which means the right-hand side of this equation is -1, right? So you might say at the next time step it dropped all the way to 0. Let's imagine for the moment it just makes a slight change in that direction, right? It's just influencing the direction that this neuron is going to change the next time step. So it changes a little bit. Now it's 0.9 at the next time step, let's say. Now what happens? The next time step.
It'll slowly taper off to 0.
It'll slowly taper off to 0, right? At 0.9, the right-hand side of this equation says -0.9. We're only making a little bit of a change. So at the next one, it's even less of a change. Less, 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 less. And it approaches but never touches the 0, right? The value of this neuron, it's initially high, it's +1, but it's gradually being pulled down towards 0 by this differential equation. What happens if we set the initial value of y sub I to -1? What's that?
Approximation of 0.
It approaches 0 from below, right? Same thing. So -1, we plug -1 into the right-hand side. Negative of -1 is +1, which means it's going to increase in value at the next time step by a small amount. And the next time step, it's going to increase by an even smaller amount. You can imagine all the values in between. All of these approach 0. So why is this term included in a CTRNN? Why place the minus of the current value to describe a neuron? Any neural scientists here? What happens to a biological neuron if it's not really influenced by anything else? Kelly?
Because the neuron can't see into the future, so it needs to know what the previous times of what was happening.
Not quite. So you're right. There's no reference to things in the future, any prediction here, right? It's just a neuron by itself, and we're sort of using this mathematical equation to approximate what actual neurons do.
Are you talking about like
Reuptake.
where if there aren't any outside, no outside stimulus, just kind of decays until there's no signal?
Exactly, right? So the neuron is lazy, right? So it starts in some excited state, and if nobody else says otherwise, it'll just gradually decay down to a value near 0, right? It says nothing's going on, I'm just going to decay back to some default value. right? It won't stay at its initial value. Biological neurons do the same thing. If they don't get any influence from outside, from neighboring neurons along incoming synapses, the neuron will relax back to some default state. That's what the minus y sub I is doing here. Okay, let's add in a little bit more. Let's add in now on the left-hand side a time constant. We've already talked briefly about tau, so we're going to come back to this here. So we're using tau for t because we're talking about time now. We see that tau has a subscript of I, and that reminds us that we're really writing an equation where we actually have a bunch of these equations, one for each neuron in the neural network, right? If we have a neural network made up of 100 neurons, we have 100 differential equations, right? But we're focusing for the moment on the ith one, the ith neuron. So this ith neuron has a particular time constant associated with it, and that time constant is on the left-hand side. So again, if you mentally divide both sides by tau sub I, you would actually get y prime I equals minus y sub I divided by tau sub I. I've just placed it on the left, following my colleagues because we're lazy. We don't want to write out a fraction. We're going to write this all as just one line. All right? So we're really dividing the negative of the current state of the neuron by its tau value. What does tau do? If you recall from our lecture where we talked about the time constant. So in the neural networks inside a pyrosim, you can also set the tau of a neuron. What does tau do? What's its function?
It's how fast it decays.
It's how fast it decays, exactly, right? So for different tau, we know now that our neuron will decay towards 0. By setting tau, we can change the rate at which it approaches 0. So let's, again, set the initial value of our neuron to +1. What happens if tau sub I is equal to 0? Actually, that's not really good, right? We've got divide by 0 then. All right, let's avoid divide by 0. Let's set tau to 0.00000001. What happens in that case?
It's going to decrease faster.
It's going to decrease really fast, right? We're dividing minus y sub I by a value that's close to 0. It's going to go really fast. And either it's going to do this, again, it depends on how we integrate this differential equation, or it might actually overshoot 0. And we know what happens when the value of the neuron becomes negative. What happens in the next time step? Bump back up. There you go, right? So this is, if you set a tau near 0, you get a Woody Allen neuron, which is any little perturbation and the thing goes absolutely crazy and overreacts and all hell breaks loose, right? Okay, so that's a tau that's near 0. What happens if we set tau equal to 1,000,000? Really, really slow. So let's set our initial value of the neuron back to +1. And set tau equal to 1,000,000, and we get, which if I keep going, it'll eventually get to 0. It'll take a while. So neurons that have a tau value that's very large are Eeyore neurons. Everybody remember Eeyore from Winnie the Pooh, right? Eeyore is pretty phlegmatic, right? Takes a lot to really influence Eeyore's behavior, right? So by setting tau manually, when we'll see some experiments where the experimenters set tau by hand, or better yet, allowing evolution to set tau, evolution can play with some neurons to make some neurons more reactive to external perturbations and others more resistant to external perturbations. We don't have any external perturbations yet, but that's tau. You can actually play around with this now. So if you go into your whatever version of your pyrosim, whatever assignment you're on, and when you send motor neuron, you can set tau to different values. So set tau close to 0 and watch what your robot does. Set tau to 1,000,000 or even minus 1,000,000. Doesn't really matter whether tau is plus or minus. And you'll see how your robot reacts. Right? Okay. Let's keep going. Let's add the piece that we're most familiar with. Right? So
Y is going to change as a function of this, and also it's going to change based on all the other neurons that are influencing it, right? So not that different from what we've seen before, right? We're now adding in all of our synapses. Okay, you can see I've left some spaces here, so there's a few more things we're going to do here. Now we're adding in our activation function, and this is kind of different from what we've seen before. Usually the activation function is sitting on the outside here of the right-hand side. Here it's on the inside of the right-hand side, which is a little odd. The reason why, this is sort of a change in notation here, is we're going to actually squash the value that's being output by y sub j. So the actual value of all of the neurons might be a value that's above +1 or below -1. So I'm going to draw it in the following way. We have a neuron, and inside that neuron is a number, which is y sub I. And again, this might be a very large, or very positive, or very negative number. But whenever this neuron emits a value, so either it sends a value out along its synapse to another neuron, or it outputs its value to a motor, because it's a motor neuron. Whenever we request the output value of this, then we're going to squash it by the activation function. So you can see here we're updating y sub I, and it's being influenced by the output values, by the output value of each of the jth neurons. Make sense? Okay. So we're never really when we're actually using the neural network to do something, we're updating these internal values, but the internal values, when they leave the neuron, then we squash it. Okay. Let's add in 2 more pieces. Actually, I think 3 more pieces. Let's add in a gain for neuron J. So you'll notice now we have G sub J. So we just have a single subscript here. So we know that each neuron in the neural network, there may be 100 neurons. Each of those 100 neurons has its own tau value, and each of the 100 neurons also has its own gain value. What does the gain do? We know that a neuron's tau influences the rate at which that neuron changes. What does each neuron's gain value do? Let's imagine there's some neuron in this neural network that has a gain equal to 0. So we have neuron J, and it has a gain of 0. Tell me about neuron J.
Always outputs 0.
It always outputs 0. It doesn't influence anyone, right? So if this is our neuron here, and it's got a gain of 0, even if its synaptic weight is far from 0, right? It has an influence on the other neuron that's great. We've basically silenced neuron J. Right? What happens if a neuron has a gain of 1 million? It's very loud now, right? We take the gain of that neuron, we value it, we multiply 1 million by the internal value of that neuron, multiply it by the synaptic weight, and out we go, right? So by changing the G's associated with the neurons, we can make the neurons quieter or louder, right? Meaning we're sort of silencing their overall voice, independent of each of their synapses. We could have, for example, a neuron that has 3 outgoing synapses. If we set all of these 3 weights to 0, we've also silenced the neuron. But we're trying to make things easier for evolution by giving evolution an additional parameter G, and by reducing that single number to 0, it silences the neuron. Or turns up the gain, makes the neuron louder. Right? So we're introducing some new terms here in addition to W. We know that we're going to place W under evolutionary control. Evolution is going to change the weights of the synapses. It's also going to change the speed of response of the neurons and the gain of those neurons, their overall influence inside the neural network. Yeah. So again, remember that we have one of these equations for each of the 100 neurons in our neural network. And these tau values, this tau value then would be a vector of 100 numbers, the taus for each of the 100 vectors. We don't, for each of the 100 neurons. We also have a vector with 100 numbers in it for the gain. So we have a vector of 100, so the volume of each of the 100 neurons. And we have a matrix of weights, right? So for this matrix, every element in the matrix, the element the element ji in that matrix, that number dictates the influence of neuron J on neuron I. So as we're building up this equation, think about how evolution is going to deal with it. Evolution is going to deal with it because we're going to give evolution a matrix W, a vector tau, and a second vector G, and evolution can make changes to either of those three data structures, right? It can tune all these different parts of the neural network. So far, so good? All right. We've now added a third vector, theta j. And again, we have a single subscript, so we know that each of the 100 neurons in our neural network has its own theta. Given where I've placed theta in this equation, what is theta doing?
It's directly influencing the value of the J
It-
neuron.
Absolutely, right? So it's really on the inside here, right? We take the raw value of yi, the internal value, right, which could be anything, and we're then adding theta to it. So what are we doing here?
We're shifting one way or the other. So like if it's a little bit negative, you could end up making it positive, and then the gain could make it even more so.
Exactly, right? So as the name implies, it's a bias. We're biasing the value of the neuron, regardless of what it is, right? Remember that y sub j and y sub I, they're changing over time, but we then take the actual raw value and we move it up or down by theta, right? So you remember back to the beginning when we had our neuron that was sort of decaying back to zero. If we have a bias, we can influence what its resting state is. Without a bias, neurons will always decay to zero if nothing else is going on. When you add in the bias, if a given neuron has a bias of +5, theta is equal to +5, it will decay towards +5. If we give a neuron a bias of -8, it will decay towards an approach but never quite reach -8, right? It's the resting potential or the resting state of the neuron. So I was telling you at the beginning of this lecture that biological neurons are kind of lazy. If nothing else is going on, they will decay to some default value. Different neurons in your brain have different default values. That's what the bias term here is trying to capture. It's going to allow, again, evolution to set different biases for different neurons so that they decay to different values. If a given neuron has a positive value or positive bias, it's usually in the excited state, right? Even if nothing else is going on, if nothing else is influencing it, its default value is usually positive, right? It's staying up. A neuron that has a negative bias, if nothing else is going on, will tend to decay towards and stay at some negative number, right? So this is important for robotics because remember that some of the neurons are motor neurons and they're going to dictate what the angle of the joint is. Maybe for your robot it makes sense to always have the lower leg slightly extended. It might rotate kind of around this default angle, but it helps, evolution has figured out it helps for the leg to usually be fully extended. If there's no sensory information coming in, if the robot jumps and all the touch sensors go to 0, it extends its leg, right? Evolution could do that by tuning the bias, right? If the bias stays at 0, then usually if nothing's going on to that motor neuron which attaches to this joint, it will stay near the default angle. So we're giving evolution a bunch of things to play with here to change the way the neural network works. Okay, last piece of the puzzle, I promise. This is, again, I've taken this from the reading for today. Not a good choice of notation here. Uppercase I sub lowercase I. And again, I apologize for this. These are different I's. They don't refer to the same thing. It's uppercase I because it's now referring to input, right? Something coming from outside. So this is our input, or in our case, for robotics, a sensor. So again, imagine that we have 100 of these equations, because we have a neural network with 100 neurons in there. Only some of those neurons, let's say a dozen out of the 100, are actually connected to a dozen different sensors. The other neurons, the hidden neurons and the motor neurons, they don't get any information from sensors. So in those first dozen equations, which correspond to those first dozen neurons, at each time step there's some number that's arriving here, which is the actual value of the sensor. It's the value that's arriving, it's inputting that value from outside. The other remaining 80 or so neurons, which aren't connected to sensors, I sub I is just set equal to 0. They don't see, they're not affected by a sensor. Okay, so using this equation, we've captured quite a bit of sophisticated neural dynamics and the connection to the outside world. What about the motor neurons? We know how to write down these equations for our dozen or so input neurons. The hidden neurons have this equal to 0, and the motor neurons also have this equal to 0. But at the moment at which we extract a value from a motor neuron and send that to a joint, we take this thing, right? We take the activation function. So if we're extracting the value of the jth motor neuron, then we do this computation, which we know gives us a value between -1 and +1, and send that to the joint as the desired angle. And away we go. Make sense? Okay. All right. That's CTRNNs. I promised you in this pair of lectures that we were going to do minimal cognition. This is not really a minimal model of the brain, but it's still relatively simple. Trust me, they get much more complicated from here. Okay. This is what we're going to use. This is the kind of neural network that's going to be used in the experiments we're about to see. And in the experiments we're about to see where we're going to evolve robots, evolution is evolving a genome. Remember, a genome is all the information that describes the phenotype, which in our case is a robot with a neural network inside. The genome is made up of one matrix and 1, 2, 3 vectors. Right? 4 pieces together, right, make up the genome. And evolution can make changes to any values in there. Okay. All right, so we've got 10 minutes left. I'm going to just talk very briefly about this particular experiment carried out in 2008. It's a pretty sophisticated experiment. So again, if you don't get all the details, that's fine. This is really more for the graduate students in the class today. But I think you'll follow the basic intuition. This project was about trying to create a robot that could exhibit functional hierarchy. What do we mean by functional hierarchy? Well, what we mean is we're going to try and teach the robot a bunch of functions, relatively simple things like start like this and grasp the cube. You can see there's this little white cube in front of the robot. That's one little function, which they also call in this paper a motor primitive. So basically a simple action, motor primitive. One is grasp the cube. Another function is move the block up and down 3 times. Another function is move the object back and left and right 3 times. Another function is push it forward and back 3 times. So can we teach a robot to do a bunch of these functions or a bunch of these motor primitives? And then, once it has, can we ask it to do a sequence? Can we hierarchically organize or sequence these motor primitives into a motor non-primitive? Something much more complicated like, hey robot, start in the home position, reach for the object, move it up and down 3 times, and then go back to the home position. Or we could ask the robot, hey robot, start at the home position, touch the block with one hand, and go back to the home position. Or this, right? We're going to try and get a robot to learn these behaviors and then be able to mix and match them into a hierarchy or a sequence. Okay, there's two ways we could do this. The first one is pretty simple. As you can imagine, because it's simple, it's actually wrong. It's not the way we probably do it. We could create 3 separate parts of our neural network, exactly like we did with our XOR function, right? We created 2 parts of the network that computed 2 subfunctions, and OR, and then combined those 2 parts together. We could train those different parts to exhibit each of these different primitives. So we're going to use these colored squiggles. Maybe the green squiggle is this, the blue squiggle is this, and the red squiggle is go back to the home position, right? So we'll use these squiggles for this. Train each part of the neural network to do those simple things, and then add on 3 more little neural parts that are gates. They will turn on and off these parts. What do I mean by turn on and off? It means that they allow this thing to affect the motors. So once the robot has been evolved or trained to exhibit these 3 things in isolation, a robot do motor primitive green, do motor primitive blue, it can do it. Then we can say do green, then blue, then red, and it will learn to turn this gate on and these 2 off, then shut this one off, turn this one on, turn these 2 off, turn this one on, and finally turn this one off and let this one on. That idea of gating or allowing different parts of the network to flow through and affect the motors, we've already seen that before. Where did we see that before? Way back at the beginning when we talked about the history of AI. We had a robot that was running around, and if there was an obstacle, it should avoid the obstacle. It should go around and just sort of explore, but if it ever gets close to an obstacle, the exploration part should be suppressed, and the obstacle avoidance part should take over the motors, right? You can explore as long as you don't get near an object at that point. Do the thing that's more urgent, which is avoid obstacles. Where did we see that robot?
The Roomba.
Not Shaky, the Roomba, right? So if you've got a Roomba vacuum cleaner at home, it will run around and move at random to make sure it cleans up all the parts of your floor. But if the cat gets close to Roomba, suddenly the obstacle avoidance piece will kick in and it will avoid the cat, right? So this is sort of the 2008 version of Roomba, which has inside it the subsumption architecture. More urgent matters subsume the motors, take over the motors if you need it.
Do you know when the Roomba was commercialized?
Let's see, 2002, 2003, somewhere around there. Okay, so I said that this is a simple way of doing things, but not a correct way of doing things. It works for the Roomba. Do you think your brain works this way? I guess I biased you, right? Your brain definitely doesn't work this way. Why not? Seems pretty simple. Why doesn't evolution find this solution? How many motor primitives are you capable of? Hopefully more than the 6 or 8 that's here, right? There's no good way to quantify what a motor primitive is in a human, right? Is this a motor primitive? Is this a motor primitive? It's hard to say, right? But regardless of how you count, there's probably millions or billions of separate things that you can do, separate simple actions that your brain can command your body to carry out. And obviously you can learn new ones all the time, right? So what's the problem here?
Take too long to compute all the different possibilities.
It would take too long to compute, not alone compute, but store, right? Where are you going to put all these things? Yes, we have a lot of neurons and synapses, but it doesn't seem like a very efficient way to store things, right? So again, we're not quite sure, but they're pretty confident that that's not really how the brain does something. There aren't different parts of your brains for all the different parts of your brain for all the different things you can possibly do. So, is there a more clever way to do this? Can we compact or compress multiple motor primitives into the same motor circuit? So instead of having separate modules in the brain, can we just have one tangled mess? And that tangled mess can produce the red squiggle or the blue squiggle or the green squiggle when commanded to by the purple squiggle. Now you'll notice that these squiggles are changing quickly and this one is changing relatively slowly, fast and slow. So we actually, this is a cartoon of a neural network. We're not actually drawing the circles and the arrows for our neurons and synapses. We have this tangled mess between fast units or fast neurons and slow units or slow neurons. Where do we get fast and slow from? From tau, right? So we got a mass of Woody Allen neurons over here and a mass of Eeyore neurons over here. The Eeyore neurons are listening to the human who's saying, hey robot, do green, then red, then blue. It hears it, the neurons hear that, and they are sort of like the conductor of the orchestra. They say, the slow neurons keep an intermediate value, and when the slow neurons have an intermediate value, remember that all the neurons are connected up here. The slow ones are connected to the fast ones. They push the fast ones into a particular pattern, which is the red one, right? So this is sort of the conductor saying, okay, when I raise my baton at this level, I want this particular melody. When I drop my baton to this level, because you guys are fast, do this particular fast pattern. I'm slow, but I'm influencing at a slow rate changes between the fast patterns of the fast neurons. Yeah? Okay, so it's the same Woody Allen neurons here that are producing the green squiggle as are producing the red and the blue. We're packing them all into that neuron. We don't have one neuron or a few neurons that are encoding red and then some others that are encoding blue. They're capable together of producing different melodies in the same way that the same orchestra is able to produce different music depending on what the conductor does. Okay, we've got a couple more slides where we'll look at this particular neural network in a little bit more detail, but we'll leave that for Tuesday. You have a quiz due tonight. Undergraduates, you're working on assignment 5. Grads, you're working on 9 and 10. Have a good weekend. Thank you.